Okay, wish you all a good morning. I will start today's session. So in the last class, we have discussed about the adaptive filters, and we will continue that discussion for a certain extent today as well. So in the adaptive filters, we have discussed about basically FIR adaptive filters. And in here, the block diagram shows a diagram of an FIR filter. And in here, the difference is that we are adapting the filter coefficients H0, H1, H2, H3 based on the feedback we receive from the output. So the values of these filter coefficients are getting adaptively changed with the time as the output as required by the output. By looking at the output, we can decide whether we need to adjust these coefficients, filter coefficients or not. So those adaptation will be done by observing the output. So in the this diagram, the second diagram, what we show is that this output of the filter is being compared with the desired signal. So assuming that we know the desired signal, we can compare the desired signal with the output of the filter. And if there's some kind of a difference, which means if there's some kind of error between the desired signal and the output signal of the filter, that error signal can be used to determine the coefficients of the filter. So the error signal is used as a kind of as an input into this algorithm, which is used to adaptively change the filter coefficients. So the algorithm will be adaptively changing the filter coefficients using this iterative process. So the iterative process that we are using will be that this current, the filter coefficient value that we are updating is equal to the past filter coefficient value and any kind of adjustments we have made to the filter coefficients, which is given by this delta HM. So once we do this update, we are expecting the final error of this process, final error signal of this process to be minimized as much as possible. So we are updating the filter coefficients and we are expecting some error to be reduced as much as possible. And the graph in here shows that the error signals amplitude changes with the values of the filter coefficients. So the target is to find the place where the error is minimum in this graph. So in this graph, we have these points in the graph, and the filter coefficient values. Based on the filter coefficient values selected, the resulting error will be along this distribution line. So once we select a filter coefficient value which reduces the error, we can call that as a better filter coefficient value. So we need to try to reduce the error as much as possible. So the target is to reach this minimum point in the function. So in order to find the minimum point, we need to consider some aspects of this graph. So aspects of this graph means like we need to find the gradient of this graph and the place where the gradient becomes almost zero. And also we need to reach that gradient position. We need to also make sure that this gradient minimum position is the global minimum position as well. So so there are two targets: finding the minimum and making sure that that minimum is the lowest minimum of the entire process. So we need to make sure that we find the global minimum. So for that, we are following certain steps. So we need to find the minimum. We need to find the global minimum. And also we need to make sure that we use a learning rate, mu, which is the step size that we are using to adaptively change the filter coefficients. So the change of the filter coefficients will happen based on the step size. We will increase or decrease the value of filter coefficients based on steps by taking steps of this mu step size. So mu is also therefore enabling us to find the minimum point of the error value. So we want to minimize the error as much as possible. So we want to find the minimum error point. So in order to find the minimum error point, we need to go to that minimum point using this updating algorithm. That algorithm will move in steps of mu. So the mu value also determines how fast we reach that minimum point, and also whether we reach the minimum point or not. Sometimes we might, so this mu value is also sometimes like losing the minimum point. What I mean is that if we consider the mu values, different mu values that it can take, if we take a very large mu value, that means the step size of moving from this point to another point is really large, then sometimes if the step size is too large, then the point in here, let's say there's a point in here in the graph, the point in here will next move to a point on the other side of the graph, which is not having a minimum, right? So to the left side. So if the step size is like that, so the resulting point will be on the left side, so that you will not be able to find the minimum because you will be moving in this left direction afterwards or some right direction, but you will be missing this minimum point in that process. So because of that, you have to choose the optimal learning rate to find the minimum point appropriately and without missing it. So those are the things I think we discussed about the adaptively changing filter coefficients. So the different matrices we have defined in here. So the autocorrelation of the input signal, which is autocorrelation of xn, we have defined using a matrix. So we know already about the autocorrelation matrix of an input signal. We know how to like mathematically model it. So one thing is this, it can be mathematically modeled as the input signal into its own transpose. Once we take that product, we are left with this matrix, which is a square matrix of dimension equal to the dimension of the input signal. So once we do that, we have the autocorrelation matrix of the input signal xn. After that, we have another matrix, which is the cross correlation matrix, which is the matrix that define the correlation between the input signal and the desired signal. So the desired signal can also be defined as a vector, and the input signal also can be defined as a vector. So once you take the product of these two signals and then you take the expectation, you will be left with a vector of certain size as the cross correlation vector RxD. So those are the things we have obtained as the input signals or input data required for our error calculation. So for error calculation, we need this autocorrelation matrix of the input signal and then the cross correlation vector between the input signal and the desired signal. And then we want to calculate the error signal, which is the difference between the desired signal and the output signal of the filter. So the goal is to minimize the error. As I always say, we try to minimize the error. So we have to find the optimal filter coefficients that will enable us to reach that target. So in order for us to do that, we have to make a relationship between the error and the filter coefficients. So we can define the error as a function which is like equal to the desired signal, subtract this output signal. So the difference between the desired and output signal will give us the error. And it can be further expanded like this, which is dn minus xtnh. So this is the way of relating the output with the filter coefficients. So now we have the filter coefficients also as a parameter of this error function. So then we have to now develop an optimization algorithm that will minimize the error as much as possible under certain constraints. So in order for us to minimize this error value, we are considering this objective function, which is the average value of the error. But also we are considering this like square value of the error in order to make sure that we are considering only positive values of the error. So normally error value can also be minus or negative in cases we are subtracting from a large value, a lesser value from a, we are subtracting large value from a lesser value. So once we have, sometimes if we have error values negative, we might not be able to get the clear idea whether there's error or not. In order to get the absolute picture or the absolute value of the error, we are taking squared values of each of the errors, and then we are taking the average of that error. So the average of the error of the system must be minimized as much as possible under certain set of constraints. The objective function that we are considering here is this expectation of the error values. Okay, expectation or mean value of the error values, and that objective function is the one that we are trying to minimize. So after that, we want to find like what exactly is this error function, uh, expectation of the error function means in terms of the filter coefficients, because we want to find the filter coefficients that will minimize this expression. So there should be some relationship between h and this function. So in order for us to like expand it further, we use the normal definitions, which are basically error is equal to dn minus yn, and then taking the square. Then we do this operation where we take the multiplication between these two vectors, and then we try to find the final expression that relates to the error. And in here it is shown the final output is equal to sigma squared of the desired signal, or the variance of the desired signal, plus the filter coefficients into input autocorrelation matrix, then out the filter coefficients and the cross correlation between the desired and the input signals. So this is the expression that we get based on what we know already. After that, we try to minimize this error and find the minimum point of this error by taking the differentiation of this value of the error with respect to the filter coefficients. So we try to differentiate with respect to filter coefficients, and we try to find the optimal filter coefficients that will make the error value go to 0, or that will make the error function's gradient go to 0. So the gradient value should go to 0. So because of that, we have found the gradient in here as GH, which is equal to 2RXH minus 2RDX. So this one we are going to make equal to 0 in order to make the gradient equal to 0 and make the error minimum. So after that, we can find from that expression, once we make this expression 0, we can find a relationship between the filter coefficients and the other matrices we know. So once we try to make the subject of this equation the filter coefficients, then we can find this the other terms which enable us to find the filter coefficients, right? So this equation is valid for scenarios where the statistics of these expressions, x signals, right? The statistics of the x process or the random process, which is defined by x, is static, right? So this equation will give us or uh, us the value of the filter coefficients that are good once these autocorrelation matrices are static. However, in cases where these values are actually varying with time, then we need to find the filter coefficients each and every time of the process and update the filter coefficient values. So as of now, we have considered for stationary processes, and therefore the values of these autocorrelation matrices and cross correlation matrices do not change over time. However, in real world scenarios, the values of the process will not remain constant, right? The mean value, the variance value, autocorrelation values of the random process will not remain constant over time. So in such cases, we need to consider like a situation where the values of the process changes over the time. So the mean value, the variance, the autocorrelation, and etc. The statistics will vary along the time. So in such kind of cases, like we need to determine the values of the filter coefficients adaptively so that the values of the changes of the input signal is taken into account. So we need to adaptively change the filter coefficients if the random process that we are considering is not stationary, right? So in the last class, we have derived this equation, and this equation we have derived mainly for stationary signals, right? For stationary signals whose statistics don't change. So once we find these Rx values and the simple RDX values, we can plug in these vectors and matrices, and we can find the filter coefficients. That filter coefficient will be taken as the optimal one. However, if we consider changes in the environment, then we need to update these two matrices and again find the H value. So that is what we are trying to achieve. So this part is about finding the Hessian of the equation which is related to error, and then finding the place or finding whether the Hessian is positive is something that is done here. So once you find that Hessian is positive, that means that the Hessian will be positive. It gives the idea that the function is having a minimum value, and also that this function is a convex function. So if the if the value of Hessian of a certain matrix is above 0 positive, that means that function is a convex function. So what I mean by a convex function, right? Do you know about convex functions? Anyone? Okay, so convex functions mean that convex functions are functions that have either a minimum or a maximum, right? So you can find a minimum or maximum. Mostly actually it is mainly having a minimum. But there's another type of functions called concave functions. Concave functions have maximums in general. Okay, so the convex function will have a minimum. So by finding Hessian, if it proves that the Hessian is positive, then we know that for sure that function should have a certain minimum, like a sort of actually a global minimum, and then we can find the minimum, right? So in order to find the minimum, we have to find the gradient and find the gradient zero values. But also we could took into consideration the scenarios that could happen in finding this minimum value. That is that this minimum value also can occur in different places, not only in one place. If we consider the filter coefficients in a certain area only, sometimes we can find a minimum value in that area, but that minimum value might not be the exact minimum value of the global process. Like once we consider the filter coefficients for a large number of uh, range or a large range, then we can find some other positions in the function also that makes the error value goes to very low value. So therefore we have to try to find the kind of the best or the global minimum point as much as possible if we have the resources, and use that global minimum point corresponding filter coefficients to achieve low error. Otherwise, sometimes if we use the filter coefficients related to point A, sometimes the error value might not be going to zero or going to converge, or it's not going to go to a small value within a short time. Sometimes whatever we do, we cannot converge the error value or make it smaller than that at all costs. We cannot sometimes do that. It's mainly because we have chosen filter coefficients that cannot do it. Sometimes we have to select a certain optimal filter coefficients that can make the error go to much minimum values. So with that, actually, I think we discussed and we came into this conclusion that the cost function we need to we need to find the cost function, and that cost function is the in here the cost function is the error value, and the error value is given by this equation that we found. So we found an equation for the error value. This function is what is we are trying to minimize. So this is the cost function. So if the error increases, the cost value increases. So the cost function increases. So the cost function is the error function, and we have considered that it has a minimum value. After that, we also have to make sure that the Rx value also is invertible. Uh, Rx means the matrix of X, which is giving us the autocorrelation value of the input signal X. And this Rx value should be invertible in order for us to find the inverse of the Rx value in this equation. Okay. So in this equation, we have to find the inverse of the Rx value to find the optimal filter coefficient. So in cases where we cannot find this inverse, then sometimes we cannot find the optimal filter coefficients. So up to this point, we have to we have to find the inverse of this, and that value of the inverse must exist for this Rx matrix. So therefore, in order for it to be invertible, it should be a square matrix, and also it should be positive definite matrix. Therefore, it has some positive eigenvalues. After that, we have to find the global minimum, and we have to find the corresponding filter coefficients for that. So the global minimum point will give the minimum error. Will give the minimum error for the system. So uh, this is how the optimal filter coefficients have been derived using these statistical matrices. So the minimum error equation we have derived also, and we have discussed how we can denote all those the error function with the known matrix values. So the adaptive filters, like practical applications we have discussed. So those are the things we have discussed. So in today's class, we are going to discuss about this filter coefficients and how we can update the filter coefficients in by in this situation. So update the filter coefficients have to be done using a certain algorithm. So there are many algorithms that can be used for that. So we can use algorithms such as steepest descent algorithm, and then stochastic gradient descent algorithms, least mean square algorithm. So those are the things we can use. So there are certain standard methods of developing that algorithm and then finding the most optimal filter coefficient values. So any questions up to this point? If you have any questions, let me know right now. So if we give a certain input signal, we can get the output from this filter. So suppose this is a filter that we are going to work with, and this filter um, coefficients are given by H values. So H1, H2, H3, H4 to HM. There are coefficients. Then afterwards we can get the output. We can compare the output with the like desired signal. So far we have considered that the xn, or the input signal, and the um, the dn are WSS processes so far. So because of this WSS nature, the values of the statistics of these signals xn and dn are not going to change over time. Because of that, the values of the filter coefficients also need not be are not time varying. So the values of the filter coefficients are also not changing, time varying. So values of the filter coefficients are also not time varying once the xn and dn values are not time varying, right? WSS means that their statistics are not time varying. So the filter coefficients, we can fix the filter coefficients in this situation as to a single set of values. So the filter coefficient values will not be changed over time. So we don't need to update the values of filter coefficients in this scenario, right? So we don't need to update the values of filter coefficients. The optimal values of the filter coefficients can be found using the equations that we found or derived earlier in the last session. So the optimal values of filter coefficients can be found using the computations found using the Wiener Hopf equations that we derived last week. So the Wiener Hopf equations we derived last week, which are basically these ones. So the Wiener-Hopf equations are given by this expression. So in here the values of the autocorrelation of the input signal is taken into account. Then the cross correlation value of the desired and input signal are taken into account. And using those two matrices, we can find the Pareto coefficients. So this is the Wiener-Hopf equation. So this Wiener-Hopf equation can be used to find optimal filter coefficients. So in cases where the things do not change, then we don't have to like find the value of filter coefficients each and every time. We can fix these values of filter coefficients to a certain set of values. So this equation we call as Wiener-Hopf equations. So Wiener-Hopf equations can be used to find the values of the filter coefficients that are optimal to the system. So the optimal values that reduce the error we can find. So once we have done that, now what the problem is actually in real world scenarios, we don't have this, WSS signals all the time. So for non-WS scenarios, where we have the, non-stationary signals, that means that the xn values and the dn values, or the input signal values and the desired signal values, can be varying with the time. So once they are varying with the time, then the filter coefficient values also need to be updated with the time, so that the optimal performance from the filter can be obtained. So for non-WSS signals, we have to derive the filter coefficients in an iterative manner. And for that, there are many methods and algorithms that are widely used. So in here, we are going to discuss about mainly two algorithms. So in today's class, we'll be focusing on those sections. Right, so the xn and dn values are time varying. So in such cases, we can define the input correlation matrix um, just as before. Now we need to find each and every value of the input autocorrelation value. So if I denote the input autocorrelation value using this R symbol, I will use capital R symbol to denote that it is a matrix. Inside the matrix, I will have components of the autocorrelation values at each time instance. So I will denote this as Rx. Inside the matrix, I can get the each element into account of the autocorrelation matrix. So we discussed and we derived this autocorrelation matrix earlier. So we are considering set of input signal samples for a fixed number of samples. So we can take fixed number of samples up to about m. So the number of elements in here is going up to n minus m plus 1, right? So suppose like if you make the n equals to m, right? In here it's m, capital M. If you make n equals m, then you should be able to get the final like sample index as 1. So the number of samples, if you make it equal to m, then that means the autocorrelation that you are considering here is the autocorrelation between the time index 1 and the n. So then, so you will be considering m time samples in one situation. So this matrix, as you know, is going to be a symmetric matrix. So the values of the elements are going to be symmetric over the diagonal. So here you can take that like this. So these values are going to be symmetric. Along the diagonal, you will have some, same values. So this will be Rxx. I mean, same values means like the values related to the diagonal will be there. So the index of the index of the signal considered will be same. If it is Rx n minus 1, then it will be Rx. Index will be n minus 1, comma n minus 1. Likewise, this indexing will go in the diagonal. And in the diagonal, the final element in here will be Rx n minus m plus 1 in comma n minus m plus 1 again. So this matrix is of size m by m. There are m samples in the x direction or in the row wise. There are m samples in the y direction or in the column wise. So in the row, in this direction, there are m dimensions or m samples, and in this along the columns there are m samples. So it's m by m matrix. This matrix is what is going to determine the statistics of the input signal xn. After that, you also need the statistics of this cross correlation between the input signal and the desired signal. So this one we denote using RxD. Input signal is given by X, desired signal is given by D. So this is a vector. We are going to consider the definition for this as well. In here, we are going to take the product between the input signal and the desired signal, and you are going to take the transpose of that vector. So in there, we will be having this vector as equal to the autocorrelation values that you obtain at each time instance from n to n minus m plus 1. So up to this time index, you will have the values of autocorrelation. So you will denote it using this RxD n comma n. So the n index compared with the n index. So in here, we are considering that the values of the input signal are varying with the time. So desired signal remains fixed, right? So we are going to compare this input signal with a constant or fixed desired signal. So we are going to assume that this is not changing. So because of that, the time index that we are considering or comparing with is going to remain as n. So the varying factor is the input signals time index, input signals values. So basically, therefore, we are only varying the index of this X signal. This is the vector that we want, the cross correlation between the so the Wiener Hopf equations are important to find in finding the values of the filter coefficient, and the values of the filter coefficients are given by the inverse of the X correlation or input correlation into the cross correlation values between X and D. So this is the basically the Wiener Hopf equations. So you need this equation to find the values of your coefficient. So in this above case that we considered, this above case where we consider the non-WSS signals, the values of the process or the values of the input signal changes with the time. I mean, values change and also the statistics change with the time. So because of that, the values of the statistics, which are basically these autocorrelation values, for example, will change over the time. So this means that the values of these metrics Rx will change over time. So the values in here, the Rx will change over time. Also, similarly, RxD will change over time because the statistics of this cross correlation between the input signal and the desired signal will also change with time, right? So once the statistics of the input signal Xn changes, the cross correlation values that it takes with other signals and the autocorrelation values it takes with its own signal will change with time. So because of this, all these two matrices and one matrix and the other vector will vary with the time. So these will vary with the time. Because of that, the H value will also vary with the time. So if we use this equation for computation all the time, then for large systems, finding the R inverse value will be computationally costly. Also multiplying with another vector which is also large in length will be computationally costly. For that, because of that, some simpler or iterative practical algorithms have been proposed to find the value of filter coefficients that are optimal for the system. So to find the optimal values of these filter coefficients, we are going to use some alternative methods rather than using this equation, right? So we do use this fundamental theory behind this equation, but finding the exact values of filter coefficients can be done using some algorithms, and those algorithms have been proven to be correct. So finding the solution to these equations that are given in this star mark is going to be challenging, mainly because the values of the autocorrelation values, elements are going to be, uh, you know, uh, is going to vary with time, and finding the inverse is going to be challenging. So finding the solution for the filter coefficients is going to be challenging. For each time, for every time index, for every time or for each time has its challenges. One thing is computational complexity is high. Another thing is the uh, statistics of the signals are not known. Statistics of the signal are not known. So because of that, we do not know the statistics of the signal, and because of those things, we cannot really determine the values of the matrix Rx and Rxd. For example, the matrices that we are considering here, which are basically Rx and Rxd. So we don't exactly know the statistics of these two matrices. So in such kind of cases, we have to go with empirical value. I mean estimations, where you are doing the estimations using kind of like testing and trial and error methods. Testing, and you're then checking whether the error is going down or not, and then by observing that you decide on another filter coefficient value. So this is like a trial and error method. So rather than going for this calculation using this mathematical equation, Wiener Hopf equation, we are going to use a simpler or a iterative algorithm that will be feasible or practically implemented, and that will also enable us to minimize the error such that we can actually compute the values of the filter coefficients with the time. Sometimes otherwise, because this equation, Wiener-Hopf equation is kind of computationally complex, then sometimes we might not be able to find the filter coefficients directly using this equation. Right? In such cases where we can't find the values of the coefficients using this equation, we are going to use some alternative algorithms. So the solution is for these challenges. So these are the challenges: computational complexity and the statistics not being known. The solution is to find the weight coefficients using two algorithms, mainly some two algorithms we are going to consider in here. So there are other algorithms also. Some of the popular ones only we are going to consider here. The solution will be to use mainly two algorithms. I mean, you can select the algorithm that is most optimal. One algorithm is the steepest descent algorithm. Another solution is the least mean square algorithm. So the steepest descent algorithm and the least mean square algorithm are the two types of algorithms that are popularly used to find like filter coefficient values in an updative manner in situations where the input signals values and its statistics mainly change with the time. So there are advantages and disadvantages of these both algorithms. So the advantages we will discuss first. So in here, the steepest descent algorithm is simpler and solves the problem of complexity. So SD algorithm is a simpler algorithm because of its simplicity. We say that it has lesser complexity than this Wiener-Hopf equations. Okay, Wiener-Hopf equations have certain complexity, and the SD algorithm has lesser complexity than that equation. And in here, this so rather than than the Wiener-Hopf algorithm, the SD algorithm has lesser complexity. In here, the least mean squares algorithm has like many advantages. So the many advantages that it not only solves the problem of complexity, but also finds optimal value of filter coefficients for cases where we don't know the statistics of the signals, input signals. So in here we can find the like filter coefficient values even when the statistics of the signals are not known, right? So the LMS algorithm can solve both the problems that we discussed just a while ago in here. So it has many advantages. It has more or better performance or better advantages than the steepest descent algorithm. So in cases where we don't know the statistics of the signals, we can use least mean squares algorithm. However, if we know the statistics of the signals, we can use the steepest descent algorithm for doing the calculations with less complexity. So any questions up to that point? So as a first step, we can focus on the steepest descent algorithm. So first of all, we will focus on that. And secondly, we will focus on the LMS algorithm. So the equation that is related to the steepest descent algorithm we will discuss now, and in that one is basically used to update the values of the filter coefficients. So I think that I told you that you can refer the related theories in the reference that I have given in the LMS. So if uh, you have that document, you will see that the equations that are used for the uh, you know so the document is in the last week. In here, in the week number 13, you have this reference, adaptive filters. So in here, there are many, you know, notes related to adaptive filters. So we are going to be focusing with, only some small, like components only. As of now, we have discussed up to this point, where we derive the mean square error equation, and we related that with the matrices. So we have derived these equations last session. So the Wiener-Hopf equations we have derived, right? So the Wiener-Hopf equations we have in here. This is the Wiener-Hopf equations that enable us to find the filter coefficients. So in here, this equation, the W means the filter coefficients. So I have taken in my notes the H as the filter coefficients. So in this note, this is similar to that. The W is equivalent to the filter coefficients. So in here, the Wiener-Hopf equations are given, and after that, there are sections related to finding the values of the filter coefficients using the algorithms that I mentioned just now. So these are the two algorithms, steepest descent algorithm and the least mean square algorithms. So related to the algorithms, that the algorithms, the definitions are given using these equations. So the in here, this equation means that the values of the filter coefficients are getting updated in this manner. So the filter coefficients are given by the W values or omega values. So in here, the W or omega value is getting updated uh, as the past values of the filter coefficient, and the mu over 2 into the uh, gradient of the filter coefficient values. So I mean gradient of the error function that we obtained earlier, right? So gradient of the error function goes into here. So in here, the values of the gradient we have obtained. So last week we obtained this one. So this one can be plugged into this expression directly. So once that is done, you can find the values of the filter coefficient with the time using this known values of matrices and the known values of the mu. So in here, actually, the you if you keep on substituting values for the filter coefficient, you can find a final filter coefficient that will converge over time. So we have to find filter coefficients for the filter that will converge over time. So that converged filter coefficient will be the optimal filter coefficients for the filter, although the values of the input signal keeps varying with the time, right? So the algorithm will be stable only if the filter coefficient values converge over time. So the converging process is also something that we need to know, and some calculations must be done in order to find the values of the mu and so on, that will converge the algorithm. And also some aspects related to least mean squares algorithm is also given in here. So in this section, the least mean squares algorithm is given in here, and its model is equal to this one. It's a little similar to the previous one. Here also we have to find the updated filter coefficients, and we have to make sure the algorithm's filter coefficients converge with the time. So those are the things related to these algorithms. You can read about all these things in this document. So with related to steepest descent algorithm, so those are the things we are going to discuss, and we are going to use to find the best algorithm or the best method to find the best field coefficients for the system. So using the models, we can find the updated field coefficients. So I will write down the models that are required to find the field coefficients using this method. So the field coefficients must be updated using this equation, where the hn plus 1 is equal to hn minus the mu over 2 into the gradient of this error function that we found earlier, which is g omega n. This is the gradient of the error function that we derived earlier. So the error function we derived earlier. This is the error function that we derived. We then try to find the error function with respect to the field coefficients. So this is the, sorry, I have denoted this as omega in here. It should be h with the time n. Since the field coefficients are varying with the time n, we always put that h in terms of n. So the field coefficients are given by h. That you need to remember. So I think by solving this equation, you can find the optimal h values that will converge over time. So using this h values that you get, you can find some optimal value over the time. Optimal value can be found that will converge, that will get converged over time. Right? So the value of the mu is also important in here, and the mu is known as the learning rate. So the learning rate determines how quickly we reach the minimum. For example, we have this kind of graph where we have the error defined as a function of the filter coefficients. So the filter coefficients can be given using h. So it's related to the h, the error can be defined. So the step size of moving along this function can be determined using mu. So the mu will determine the step size of learning. So if the mu is small, then you can go small steps. If mu is large, then you will go large steps. So if you go large steps, sometimes you will, just ignore this minimum point, or you will lose this minimum point in your learning process. So the minimum point can be lost, or you will miss the kind of the minimum point if you go in large steps. So the mu is also therefore important for us to find the optimal failure coefficient, which will minimize the error. And we have to make sure the learning rate is also in a certain good range, such that the minimum can be captured. So the gradient value and the mu value and the past failure coefficient value are needed for us to find the current failure coefficient, or the failure coefficient that should be adapted to the filter in the future time instance n+1. Right. So I hope that this figure is in your mind in that situation. So the filter that we are trying to optimize is this one. So we do the calculations using the whatever the algorithm, SD algorithm, and we input that into this filter. So we update the filter coefficients in here using this SD algorithm. So the value of the filter coefficient that we are updating into this is known as hn+1. The one that we are giving as output is hn+1. The previous one, which was already there in the filter, is hn. Right, so this is the previous filter coefficient, and this one is the adaptive. So the what do you call this? The newest filter coefficient. The newest filter coefficient that will be added to that will be updated in the filter, right? So this filter coefficient will be updated into the filter. The filter coefficient will be updated in the filter. So this is the equation for that, and we can expand this GHN expression. So this is the gradient expression. So this input autocorrelation matrix and cross correlation matrix are used to find the gradient value of these filter coefficients. So once you have that value, you can plug it into this equation and you can find the final filter coefficient value. So in this instance, we are assuming that we know the filter coefficient values at the time n. So this is like a trial and error method. So initially you start with some filter coefficient values that you prefer or that you think is suitable for the system initially, and then you keep updating the values of filter coefficients based on these values that you get for the like gradient and the value of the learning rate. So if you get a converged filter coefficient value, then you're fine, and you can find that you can use that converged filter coefficient value as the optimal filter coefficients for the filter system. So the goal is to find like filter coefficient values that will converge over time. So once we have the kind of converging filter coefficients, the, the filter coefficients convergence will enable the algorithm to be stable. Right? So it is also um, kind of advised to find the mu values kind of small as much as possible, such that the like the minimum point is not lost. So we have to make sure that that point is also kind of remembered. So we have to select the learning rate, select the like step size of the algorithm, such that the um, so, so, so select the step size of the algorithm as much as step size as small as possible, so that uh, small as possible, and also optimal, such that the process will not miss the minimum point. Also, this value also not only it should be also sufficiently large, such that also should be sufficiently large such that um, the algorithm quickly converges. So the mu value should be chosen such that it is small, but also not that small, such that the algorithm quickly converges. So this the optimal value should be considered or decided based on the trade-off between the between the value of mu being small and also mu being sufficiently large, such that they don't avoid the minimum, and also the algorithm is converged with quick time delay or without much delay. So the mu value should be concerned with all the two conditions. The algorithm should converge, and also the algorithm should not miss the minimum point. So those things can be considered when deciding the mu value, the learning rate. So the goal is to find the, values of the filter coefficients that will converge over the time. In order for us to happen that, as I said before, the converging will have to happen by considering these two factors related to the mu. So we can find values of mu that will enable the converging to happen, right? So by considering these situations or conditions that I just mentioned, these conditions that I mentioned, you can find the values of mu that will not miss the minimum point of the error values, and also you can find the value of mu that will converge the algorithm as quickly as possible. So by considering all those situations, you have to find the optimal mu value that will satisfy both these conditions. Should be small, but also not be too small, such that the algorithm is quickly converged. So we have to get the criteria to uh, find the optimal mu value that will satisfy this algorithm convergence. Optimal mu value or optimal step size. So in order for us to achieve the convergence, the condition should be satisfied according to this. So the delta H value that we introduce in here must go to 0. So Hn plus 1 equals Hn. Let's say this is equal to delta plus delta Hn. So this minus mu over 2 GHN part can be written equally as plus uh, some kind of a step value of the filter coefficient value, which is delta Hn. So plus delta Hn denotes this part that is added to the filter coefficient. So the filter coefficients can be increased using this delta Hn value. So once we make the delta Hn value goes to 0, then the values of Hn and Hn plus 1 will equal. And that means then this algorithm will converge. Right? So the algorithm will converge once the once the values of the Hn and Hn plus 1 are equal. So when I consider these delta Hn, it will be the difference between the optimal value of the filter coefficient and the past values of the filter coefficient, right? So this delta Hn value we can take as the difference between the optimal value of the filter coefficients that you are going to find and the current value of the filter coefficient. So this once you plug this into this form equation, the this form equation will equal to Hn plus 1 equal to the optimal value of filter coefficient. Our goal is to make the Hn plus 1 equal to the optimal values of the filter coefficients, which is Hn plus 1 equals to H naught. This is our optimal goal. In order for this to happen, the delta Hn value should equal the H naught minus Hn. So by considering that, we can write some couple of equations for the delta Hn. H naught minus Hn value we can write by using the equations we have for the using this equation we can write for Hn. We can using this equation we can write the expression for Hn. So we can substitute the values for the Hn minus 1. We can substitute values for this one. So there's a bracket in here. So that is why there's so if I'm going to consider this Hn minus 1, I can take from this equation and it will be equal to 2Rx HN, HN and minus 2RXXDN. Since there's 2 in both expressions, I can remove the 2 by cancelling out with this 2 which is in the denominator. So I will remove the 2's that are available in this equation as additional, and then I will write the rest of the expression, which is Rx. This can be further simplified by using Wiener-Hopf equations in here. Rxd, for Rxd, we can put the Wiener-Hopf equations and we can write that um, that Rxd is equal to capital Rx into H naught, which is the optimal field coefficients. So this comes from the Wiener-Hopf equations. So this in here you can see that H naught minus Hn minus 1 can be again in here you can take Rx also outside. So mu Rx comes into the outside and H naught minus Hn minus 1 remains. In here you can take this as delta Hn minus 1. And in here also you can see the same thing, delta Hn minus 1. So in order for us to find the values of the h delta hn goes to 0, we have to make this expression go to 0. So before going to making it go to 0, we have to expand this further in order to get a single equation, which is of single dimension to work with. In here, we have a matrix of m by m. So when we are working with this matrix, it's going to be difficult to make this expression go to 0. So in order for us to simplify this further, we can take this inside elements of Rx also into consideration. So we have to consider some things related to the Rx matrix to simplify this further. So one thing is that um, we have to consider the fact that it is a symmetric matrix. So Rx is a symmetric matrix. And Rx can be therefore denoted using an matrix which is like X into like another matrix and X transpose. That means that we can decompose this Rx matrix into 3 other matrices given in here. So we can decompose this Rx matrix into 3 matrices: X, this lambda. So I mean this Latin uh, letters which is giving the symbol related to we consider that lambda, and then X and transpose. So then we can write this Rx in terms of these 3 matrices. So we can denote the interior of this matrix using simpler terms. We can simplify the delta Hn term. The delta Hn term can be written so we can write this in this term. Also, we can get another relationship from one that if you have Hn, you can iteratively write that so in here I have to consider in here by considering the order of the matrix placement, I have to keep the Hn matrix at the back of this expression, because in here the Hn minus 1 is at the back of this mu Rx. So in order to retain the matrix properties, I need to keep it in here. So I have to make sure they are in correct order. So sometimes you have to like consider the order of the matrices when you're writing the matrices in order to get the correct effect of that. So in here, the delta Hn minus 1 is at the back. So uh, using this equation, we can derive some iterative equations. So I will write those iterative equations here. mu Rx into delta Hn minus 1. Similarly, we can write for delta Hn minus 1 something like 1 minus mu Rx into delta Hn minus 2 likewise. So for other also I can do the same thing using the same relationship. So this will go on until I go up to the point where delta H becomes 0. So delta H 0 point is reached. So I can write that using this method where I denote the delta Hn as a power of multiple n components of 1 minus mu Rx and then multiply with delta H 0. So this is the expression that you get once you consider all these expressions and the pattern that is shown by this difference of difference of filter coefficients equations, so delta H equations. So from this I can get that this delta H0 must be multiplied with 1 minus mu Rx to the power n value to get the value of delta Hn. So this one I can plug into the equation in here where I decompose the Rx into several matrices. If I consider this part, this section only related to this matrix. So these are mathematical matrix operations. So I can simplify this further into the eigenvalues of the matrix that we are considering here, which is Rx. The eigenvalues of the Rx matrix I can consider, and I can further, write this expression as 1 minus mu lambda. So I can take the eigenvalues of this matrix separately and I can denote that using 1 minus mu lambda, and then I can remove the the other components separately. So I think I will denote that using this. So this matrix is going to be equal to 1 minus mu lambda, where lambda is one of the eigenvalues of the Rx matrix. 1 minus mu lambda. Okay, so once you find the eigenvalues of the matrix, you will find values of lambdas for this Rx. So that lambda values are contained in this matrix. So this matrix is one of the submatrices of Rx. So Rx has some lambda values, lambda 1, lambda 2, likewise it has some lambda values in here. since it is symmetric, and we have like symmetric matrix conditions, the eigenvalues, so the values of eigen that determines this matrix will equal to 1 minus mu lambda, and the eigenvalues will be placed in the diagonal of the matrix 1 minus mu lambda. So the eigenvalues will be same, and it will be along the diagonal of the matrix. And the other matrices that are given by capital X are actually not related to eigenvalues, but they allow us to find the value of Rx. Rx is a combination of X, this lambda, and X transpose. So the lambda matrix contains the eigenvalues of the Rx matrix. So Rx matrix has these eigenvalues. So by considering this scenario, we can write the delta Hn as power of 1 minus lambda Hn. Sorry, 1 minus mu lambda. So I can write this once I have considered all these operations, metric operations. I can write this as 1 minus mu lambda n, some kind of a 1 minus mu lambda into n expression. I can denote in terms of this expression, this delta Hn. I can say it is corresponding to this 1 minus mu lambda expression. Also, this is multiplied by this. So all these, effects of all these, matrices and components have to be considered. So by considering all that, I can write this, all these vectors like X and the I minus mu lambda into N, then X transpose, then this delta H naught. So the ones that we can control in here, we are going to be concerned about. So the values of mu you can control in this system, right? So the values of mu you can control in the system, and therefore you are going to focus on this part mainly. So in order to control that, we can make it, in order for us to make the delta Hn value go to 0, we have to make this I minus mu lambda n goes to 0. So I minus mu lambda is a matrix, and that matrices, values must go to 0, which means that 1 minus mu lambda should go to 0, basically, right? Or it should be made to go to 0, or it should be made to go to 0. So in should be made to go to 0. However, like it should be made as small as possible. So in order for us to get a value for mu, we are going to go and consider that this 1 minus mu lambda value should be like a very small value, which is between 1 and minus 1. So the reason for this is that we have to get a value for mu as well. We cannot make mu 0. We cannot make this mu value equal to 0. Mu should be a value which is above 0. So because of that, in order to avoid that, we are going to make this 1 minus mu lambda expression below a certain 1, or below a certain value which is 1. So by doing so, we can get a value for mu which is between minus 1 and 1. So that will be a small value for mu. So by considering this condition, we can obtain a value for mu. So 1 minus mu lambda should be between 1 and minus 1. And in here, this is the absolute value of 1 minus mu lambda. So by solving this equation, you can find the like maximum and minimum points of the mu value. In here, we are not considering the equal sign. We are going to make the mu value below 1. So we are not going to consider the equal sign. We are going to make it lower than 1 and bigger than -1. And by considering these two, conditions, we can find the values of lambda or values of mu, which is suitable. So we can find the values of mu. So by considering the left hand side, only, I can write that 1 minus mu lambda should be above -1. So by taking the mu to the left side, I can say it is equal to 2 over lambda. So that is one expression. Another expression is finding the mu value that satisfies this right hand side, so which will be this side. So by considering this situation, the mu value will be above 0, because 1 will be cancelled in both sides, and once you take the mu to the other side, you will be left with mu and lambda, and once you are dividing both the terms by lambda, then you will be left with 0 is below mu. So by considering these two factors into consideration, you can come to a combined decision that mu should be below 2 over lambda and above 0. So this is the condition that the mu should satisfy, and this is the condition that should be satisfied in order to make the convergence easier, right? For convergence of the like field coefficient algorithm, right? For convergence of the LMS over the steepest descent algorithm, we have to consider this criteria to be satisfied. So whenever we are using the mu value, you have to check whether the mu value is between the uh, 0 and 2 over lambda values. So the mu value or the step size value that should be used must be satisfying this condition. The step size for the SD algorithm should be following this criteria such that this algorithm is converging. In here, this the lambda values that you can take can be in here the in order for us to consider the smallest possible mu value, you are considering the maximum lambda value that you can take from your metrics into consideration when you're considering the mu value. So the maximum lambda value should be considered in here when deciding the maximum limit of the mu value. So the lambda max can be considered in here when deciding the upper limit of the mu. So there could be multiple lambda values to the Rx matrix, right? So the lambda values means the eigenvalues of the Rx matrix. There could be multiple lambda values. So lambda 1, lambda 2, likewise. There could be a minimum eigenvalue and a maximum eigenvalue, and the maximum one is input in here. So the step value size for the algorithm should be defined by considering this kind of a criteria, and that once you do that, it is expected to converge. Any questions up to that point? Okay, if you don't have any questions, I think we can proceed. So the next thing is that once you decide these mu values, once you decide the mu values for the algorithm converges, the algorithm will converge over time. The error values of the algorithm will converge over the time. So if we have the error values, which is like this, which is given by this expression. So I will just say error value, the mean squared error value that we have. This error value that we have will converge over the time once we set the optimal, filter coefficients as we discussed using the algorithm, SD algorithm, and the mu values that we have decided. So the error value will converge to a certain value after some time. Okay, so with the time, the error will converge. So this is the kind of the expected goal of this exercise of SD algorithm. This is the goal of the SD algorithm. You start with a high error value and then you slowly decrease the error value over the time until the error will converge to a certain fixed point. So the goal is to reduce this error as much as possible as well. So this is the minimum error that you can take from the system, the minimum error value that we can take from the system. We have decided also, right, the minimum error value that we have decided earlier. I can give you this equation in here. So the minimum value of the error we have found, the minimum value of the equation error value we have found, that is given by this equation, right? The minimum error is given by this equation. So this value can be obtained using that algorithm, and we can find the minimum value of the error. You can get the minimum value of the error at a certain point once you obtain the optimal optimal filter coefficients. Once you input the optimal filter coefficients, this error value will be obtained. So optimal filter coefficients will be obtained once this error will converge, right? So this error convergence is something we are targeting. So as I mentioned, there's another algorithm that can do the same thing, which is the least mean squares algorithm, right? So this is about the steepest descent algorithm. The next one is the least mean squares algorithm, or LMS algorithm. It is an algorithm that can solve two problems in here, so therefore it is important. The algorithm's functions are also similar to steepest descent algorithm. Only difference is that more than relying on the statistics of the autocorrelation matrices, the least mean square algorithm uses the observed values mainly to converge the algorithms and then find the optimal filter coefficients. So the least mean squares algorithm is similar to steepest descent algorithm. Least mean square algorithm similar to the one that we discussed. The model will change a little bit. The model will be that its filter coefficients are updated according to this hn plus 1, which is updated filter coefficients, equal to the past filter coefficients plus the mu value, the learning rate, the input signal xn, and the error signal en, right? So these are the things that are used to update the filter coefficient values. The block diagram of this filter will be like this, where the filter coefficient values will be updated over time. So the input signal that we give is xn, the output signal that we get is yn, and then you take the difference between the desired signal and the output signal, and that error signal is used to give a feedback to the algorithm and to the filter coefficients, such that the adaptively you are changing the filter coefficients values, right? So your values are changing the values of the filter coefficient adaptively by changing the values of the n plus 1 using a certain algorithm. So you are finding the hn+1 using this LMS algorithm in this instance. And this is also very similar to the steepest descent algorithm. Only thing is that in here you're going to consider this xn into en, and you're going to consider the values of error directly, and you're inputting that directly into this algorithm, and then you're measuring how the values of the output converges, or the output of the filter coefficient values converges. So for this also we can do a similar analysis related to the convergence of the filter coefficients. So the convergence will again show us in here also that the mu value in here that we choose must be below a certain 2 over lambda max value. For this algorithm also we have the step size as equal as the SD algorithm. This is the condition for the convergence. So the convergence condition, and the mu value should be selected according to that. So the mu should be selected according to that, and should be used to converge the algorithm accordingly. So this LMS algorithm is a very simple method, and the simplest of the gradient descent algorithms. You can, I think, find more about the gradient descent algorithm. So which is similar to this steepest descent algorithm, and this gradient descent algorithm, stochastic gradient descent algorithm, is a very powerful and very efficient method of finding the minimum of a certain a function. The stochastic word is meaning that you are using random signals or random points, and then you are considering the error value at that random point, and based on the error value you just make the decision to like uh, I mean move iteratively into the next point. So the random point selection of the data samples is done in here in this stochastic gradient descent algorithm, so which is another like main algorithm which is used to converge or used to find the minimum of a function, error function, and then converge the values of the filter coefficients into a certain fixed values. So LMS algorithm is a gradient descent algorithm, and specifically it is part of stochastic gradient descent algorithms. So that is something that I would like to mention, and you can refer more about this LMS algorithm in the reference book that I have given you. So refer more using the reference algorithm that reference book that I have given in the LMS. Okay, so any questions up to that point? If you have any questions, let me know right now. Okay, so I think the next section will be about a new topic. Which is about stochastic models for time series analysis. Stochastic models for time series analysis. So we discussed about filters, and now we are going to discuss about this time series analysis. So what is the meaning of this? Why do we learn this? You will ask. So time series analysis is is the process of uh, is the process of analyzing or studying the behavior of a certain process that varies with the time, and you just watch a certain process over time. So the time series analysis is about observing a certain process over time. You are collecting some signal values against the time. So if, for example, you are collecting values of a certain sound signal varying over the time. So you're observing that amplitude varying with the time. So let's say I just try to just draw a signal. So in here, let's say we have some samples that we have obtained of a certain, let's say a sound signal. Let's say it's a bird. If we have a certain sound signal of that bird, so we have this sound signal. And sometimes we want to find the rest of the signal pattern. We want to forecast what is going to happen next. So from this point onwards, we have to forecast the next things. So for doing the forecast, we need to know the pattern of the original signal. So we have to know the mean average of the signal, and the autocorrelation of the signal, the kind of the similarity between the signal points. So those values, like the statistics of this signal, we have to know in order to predict the behavior of the signal in the next time instances. So time series analysis is something that is used to predict and forecast the uh, next values of the signal. And for this, we are using different methods. So we are using different models to do this time series analysis. And on top of this, now we are going to consider stochastic models. So the word stochastic means it's random. Words random or stochastic means the same thing. So the stochastic means that we are considering some random signals and into account in this instance. So we are going to consider random signals into account, and then we are going to observe its properties, and based on that we are going to predict the next values of the signal by uh, by I mean by using the statistics that we have computed. So the random signals are what we are trying to observe and predict. So the random signals are some things that we have, I think, discussed over the last sessions extensively. I think from the first couple of classes, we have discussed about random processes. So the prediction of random processes is what we are trying to achieve in this. We are going to build some mathematical models that help us predict the behavior of random processes. So we discussed about random processes, but we did not discuss how we can predict the next outcome using this, um, you know, uh, using a certain mathematical model. So for predicting, we can use some models. Some of the models include some famous models, and we are going to be concerned with only several models. So the procedure of using known data values to fit a certain time series with a model, and using that model to estimate corresponding future parameters, or like parameters of the next time instances. So we are going to predict the next signal values, the future signal values. The objective is to objective of the time series analysis is to understand the nature so objective is to understand the nature of the time series, and then using the nature you can find the future of the series. So we can forecast the future of the time series. So there are several models that you can use to predict the future. So time series can be predicted using different models. So one such model is the ARMA model, or this auto regressive and moving average model. We are going to be talking about that. So auto-regressive and moving average model. This is a process that combines the models of auto-regressive model and moving average model. So this model is a combination of auto-regressive and moving average models. So there are models which are called moving average and auto-regressive models as well. So we will learn about that. So auto-regressive and moving average model, or ARMA model, is combination of auto-regressive model and the moving average models. So as I said before, this ARMA model is used to predict the future time signals, future of a certain time signal. So we are going to use these models, AR and MA models. And also we are assuming some things in this forecast. So we are assuming some things like, we are assuming that this time signal that we are observing is a stationary signal. So initially we are assuming that the time signal that we are considering in this situation, the time signal is a stationary time signal. So what do we mean by stationary? Is that right? The stationary, I think we discussed earlier. So what we mean by stationary is that the statistics of that signal does not change over time, especially up to the second order. The mean value, the autocorrelation value, the cross correlation value, those things don't change much over the time. If that is the case, then that signal's known as a stationary signal. Its properties are stationary over the time. Right? So for such kind of stationary signals, such kind of signals whose properties remain stationary over time, we are introducing this ARMA model. Right? So you might ask, like, why are we always doing for stationary signals first? It's mainly because it is the most fundamental signal type. After that, once we have a accurate model for the stationary signal, then we can move on ahead for the non-stationary signals. And then we can propose models for the non-stationary signals by incorporating the small changes that happen based on, compared to the stationary signals. So ARMA model is going to be proposed for this for a stationary signal, right? For the baseline stationary signals, not for the non-stationary signals. That is also something I think that you need to remember. Right. So before talking about the ARMA model, we are going to be first talking about the autoregressive model and the moving average models to get a good idea about how they function, and then finally understand ARMA model or ARMA model. So AR models we are going to first talk about. AR means autoregressive model. So this AR model can be defined in a certain manner. So autoregressive model is used to mathematically like show how a certain time series is functioning. Okay, so I think there are some like things to understand in here. So so this is about the random processes that we discussed earlier. So I think that uh, in those classes we discussed how the time of a certain random process, time can be considered as a variable, right? So it's a time is going to be uh, time instances. Each of the time instances are considered as variable, random variables in that process. If I'm going to explain that again, I think I have to draw that like diagram that I always draw, where you do a certain random experiment in here, and you obtain results from that random experiments over multiple realizations. So for a random process, you will have multiple realizations. So there is realizations for each situation. So in cases where you are doing the random experiment, where you are trying to find the SNR values or received SNR values from a phone call, for example, then you are trying to find the received SNR values, and you are going to take multiple calls, phone calls. So you are going to take random phone calls over multiple times. So the first call will be one realization, call one, and call two will be another realization, call three will be another realization. So likewise, all the different random calls we call as different realizations. For those different realizations, you will obtain amplitude versus time plots for the signal received strengths, right? So whatever the received strength of the signal, you can denote using the amplitude versus time graphs. For all the different calls, you can do the same thing. Amplitude versus time, you can draw, you can plot. So for each of these instances, you can draw these plots. the amplitude I'm taking as a plus value. So each of the time instances T1, T2, T3, T4 are random variables in this process, right? So I hope you can remember T1, T2, T3. All these are random variables of the process, the random process, right? So random process. Sometimes the statistics of the T1 time instance, like mu value, for example, mu value of the T1 time instance can be equal to the mu value of the other time instance. That is in the case where this random process is a stationary signal. Otherwise, like if it is not a stationary process, then the values of the mean that you obtain for a certain time instance can be different to the value of the mean that you obtain to another time instance, T2. So T1, T2 can be two separate, totally different random variables. Right? So therefore this kind of a time series signal, this is a time series signal, right? So this kind of time series signal will depend on this T1, T2, T3, T4, likewise random variables. So we need to consider that also into our consideration when we are trying to forecast the time series signal. We have to forecast based on the past values we have got for each of the time variables T1, T2, T3, T4 likewise. So we have to predict the current or predict the next time instance value based on the past values. So the prediction has to be done, and then you have to also understand the relationship between the current value of the signal and the past values of the signal. So the model that is defining that relationship is known as this autoregressive AR model, right? That shows the combination of or the relationship between the current amplitude value with the past amplitude values, and also the effect of noise in that. So the AR model can be defined of the form AR model, which is can be of the form. In here we denote that AR inside brackets P to show that it is a AR model of order P. So why do we say order P? Is that we are considering, if we consider P number of past values, we consider that the AR process is of order P. So number of past values that we consider. So number of past values we consider, we name as P. That is the amount P that we are considering. Okay. So the general model for the ARM process, autoregressive process, is this process where we define the variable at time t, xt, in terms of past values of x. So xt1, xt2, likewise. We are defining that in terms of a linear combination of past values. So in here, I can denote it as phi1, xt1, xt minus 1 plus phi2, xt minus 2. Likewise, I can write. So in here, the W means a random error or a random error um, that is used to denote the fluctuations in the amplitude values. So random error is also added to show that some fluctuations can be added to this measured amplitude values, right? So measured amplitude values will have some error that error is represented mathematically and modeled using this W value. So this random error can be similar to something white noise. It can be similar to white noise. So the xt is known to be a assumed to be a stationary process. And the values of the W is determined by its mean and variance. So its mean is assumed to be 0 and its variance is assumed to be sigma squared W. And the values of phi 1, phi 2, phi 3, likewise, those values are based on the model parameters. So these are the model parameters that that define the combination. So we can find the model parameters as well, or else we can find the model parameter values from observation as well. This is related to the AR model that we have. So the AR model that we have is defined by these parameters xt, and xt gives the value of x process at time t. Xt minus 1 gives the value of the random process at t minus 1. So it defines the like amplitude of the signal at t minus 1, and this actually gives the value of the signal over all the this denotes the value of the signal over all the realizations considered. So this xt is the random variable at time t. Xt minus 1 is a random variable at t minus 1, and then xt minus 2 is the random variable at t minus 2, and xt minus 3 is the random variable at t minus 3, and so on. So this is the like a mathematical representation of this variables combination. Okay, so xt minus 1 denotes the random variable that constitute of all the signal values that you take at t minus 1. So the combination of all the signals at that t minus 1 is depicted using xt minus 1 variable, and it has its own statistics, and it can be determined using its probability density function if we know that, and its other characteristics like mean value, autocorrelation value, covariance value. Likewise, such kind of statistics can be determined using this variable properties. So this is the kind of the model of the AR process. So in here we have to remember that up to p past points, like p is the number of past values considered. So that means p number of lags considered. So the number of lags considered is equal to p. Then afterwards we can, so that is regarding the definition of AR model. Then we can estimate the values of phi 1, phi 2, phi 3 up to phi p, and then we can find any characteristics related to the random process xt. Right? If we know the value of phi 1, phi 2, we know the value of phi 1, phi 2, phi 3 likewise, then we can deduce the properties of the x, right? Phi 1, phi 2, phi 3. If we know those things, then we can deduce the value of properties of xt. the properties of xt we can deduce. We can deduce if we know these values. So there are many methods of reducing the properties of xt. So the methods of doing that. So anyway, we can find the values of values of phi 1, phi 2, phi 3, up to phi 5p. You can estimate those using some estimation methods. So we can estimate these parameters using estimation methods. So the one of the estimation methods is Yule-Walker method. Yule-Walker estimation method can be used, and maximum likelihood estimation method can be used. So least squares estimation method, the maximum likelihood estimation method, and other Yule-Walker methods can be used for estimation of these parameters that are unknown in this model. So those are the estimation methods that can be widely used, and you can use that to solve the unknown parameters in this AR model. Any questions up to that point? So going ahead, the next thing is about the moving average models. Moving average model, right? So this is like the AR model, as I said, it is a combination of a autoregressive model and the moving average models, right? So autoregressive model is something we discussed now, and it can be defined using this mathematical equation. And it can be, like this is a combination of past values of the time signals, right? Past values of the time signals, and past values of this random process. So the values can be given by xt1, xt minus 1, xt2, xt minus 2, xt minus 3, likewise up to xt minus p. Then you can also add a error signal or error error component in here, which is like error signal, that also can be added in here, because in order to compensate for any kind of errors that we have done, we have added by by when we were observing values and when we were calculating values and so on. So to like compensate for any error in the that we have we have made in the observations of all these values in this equation, we can compensate using this white noise that we added in here. So basically the equation that we need to consider is this equation where xt is equal to its past values plus its white noise. Then you can use these estimation methods to estimate the unknown values in that model. So moving average model, So that is a model that considers the effect of the white noise on the process of the time series. So the moving average gives us more details regarding the added noise into the system and how the average of the model changes based on that noise. So moving average model gives us an idea about how the noise can affect the um, time series signal that we are trying to study. So the time series signal we are studying can have some noise in it, and that because of that noise the average value of the time series signal will change with the time. So such kind of effects can be mathematically modeled using this moving average model. So the current limitation that we can see in the AR model is that we are ignoring the effect of the noise on the signal. In the time series signal. Let's say in the time series. So what we mean in here is that there is some considerable impact from the previous, previous random noise or random noise components, right? In the current to the to the current. So there's a there's a significant impact from the past values of noise into the current xt value. The moving average also can be mathematically defined. So that definition is given as xt equals the past values of the noise, and so I will write down its equation, and it's also can be defined using the number of lags that we are considering to define the current, uh, current value of xt. Current value of xt can be defined based on the past values of noise. The past values of noise we can give by wt plus so in here in the previous equation, I think we defined this as just w. We can define it as specifically what time instance is affecting the noise of the process, right? So we can specify that as well. So moving average means that you are defining the current xt value based on the past noise values you have observed in the system. So wt is the current noise value that is affecting the observation xt, and past noise values are given by wo omega t minus 1, wt minus 1, and theta 2, wt minus 2 likewise. So in here we are taking samples of up to q past values. So about Q, past values are considered of noise, and therefore this model is known to be of Qth order. So this model is known to be of Qth order. So this it can be defined like that. So right. So model of Qth order. The order is defined based on the number of past values you have considered. So this MA model is of Qth order. So this T1, T2, T3 up to TQ, theta Q are basically parameters of this model. And the W is given as a random process, which is having mean of 0 and certain sigma value. So theta 1, theta 2, those values are parameters of this equation. Theta 2, theta 3 up to theta value of Q are known as parameters or like parameters of this model. The W value has a distribution of mean value 0 and sigma value of sigma squared, some W value. So it could be some fixed value. Mean of that value will be 0. The process will be 0. Then the difference that we have with this MA model with the AR model is that in MA model, we are considering white noise only, which is affecting the, XT signal. So the white noise is a signal which cannot be observed. So W cannot be observed clearly, or we cannot measure it really. We are assuming that W has this distribution and has this impact, but we cannot really measure it, and therefore cannot observe it properly. So W is not a observable signal. It's not a measurable signal that much. So this is some kind of mathematical assumption, and we are assuming that these components are getting added to the current XT signal and affecting its properties. So this is not a observable thing, and that is why this model is different to the other models. So where the other model is actually measuring the XT values and past XT values. So the combination of this moving average model and the AR model, or the autoregressive model, results in the ARMA model. So in this these models are the ones that will be combined to define the ARMA model. This so this is the first equation. This is the second equation. So these are the two models that we'll be considering. So by combining these two models, by combining the effect of combining the one model and the two model, the ARMA model is defined. The ARMA model is defined as the combination of both those things. So definition. is that value of xt is determined based on the wt value, wt in here, plus, so in here it should be wt. The w at time t. W means the random noise. So the random noise that is added at time t plus the past values of the input, xt signal, past values of the xt signals I can get as I equals 1 into to p, and then phi I, and then x t minus I. So all the past values of x that we take up to p values, p lag points, p lags, and then we consider values of white noise, past white noise components that we consider up to q values. So theta values we consider theta j is up to wt minus j. So values of noise up to like q points, q lags we consider in here, right? So the noise components up to q lags we consider in here. So those are the things that we are using to define the ARMA model. So this is the definition of the ARMA model. So I will write in here ARMA model like definition. So there are some parameters in here which are phi and theta. We need to find those parameters to define this model correctly and like sufficiently completely. So so those are the things that we need to find in this model, and some limitations are there in this model, ARMA model. So the limitation is mainly assuming that the process xt is a stationary process. So assuming that the time series process, right? Time series process is a xt is a stationary process. So sometimes the actual scenario, in the actual scenarios, the xt process might not be stationary. It might not be having stationary statistics all over the time instances. But in this situation, we are like proposing this model only for the stationary process. But there are other models such as ARMA process, which is additional of this, some additional components are added into this model, into that model. And that model can like identify the effects of the non-stationary behavior of the process into the model and add that into the model and then use that to make the necessary predictions. So the solution will be like models such as ARMA model, which considers so the ARMA model considers the effect of non-stationary processes also during the time series analysis. So the finding of these parameters is the challenging thing. So finding these parameters can be done using estimation methods, as I mentioned. So one such estimation method that we can use to estimate the parameters is this Yule-Walker method. Right? So Yule-Walker method can be used to estimate the parameters of this ARMA model. So that that is the method, that is one of the popular methods that we can use to find the parameters that we don't know about this model that we have developed for a certain process. So the usage of Yule-Walker equations require us to know some, like relationships between the autocorrelation value of the process and the autocorrelation, and the, variance values of the process and so on. So we need to develop some relationships regarding the random process in order to use this Yule-Walker method. So we will discuss about the Yule-Walker method and how to solve the unknown parameters using that method in the next session. So I think by today's session, I will end by this point. In the next session, I will continue with that. I will continue from this point. So with that, I would like to end today's session. Any questions up to that point? Or any questions related to the module if you have, let me know right now. In the next class, I just want to mention that I will do some sums related to these sections that I have covered, especially these filtering, adaptive filters, and these ARMA processes. I will discuss as sums. I will do some sums in the next class. So during that class, I will be doing some sums. And so if you have any questions related to any, such sums, you can ask them during the class.